I'm going to finish up with development and plasticity as quickly as I can, given that I want to say some certain things, and so we can get into vision today. And I'm just briefly coming back to this slide about how those axons are doing this kind of pathfinding because of chemical gradients, but they're not achieving perfect accuracy. So what we're doing is we're starting out with many more neurons and synapses than we need, and then we're going to, so we have that proliferation, synaptogenesis, and we're going to prune some of that away, and we're going to see some apoptosis. And a lot of this is really influenced by the neurotrophins. So when I am a postsynaptic neuron and I am receiving a strong signal from a presynaptic neuron, I'm going to release neurotrophins during this time, so that during this neural development, so that the most successful axons and synapses are going to be what survive. And one thing I did mean to mention on the last slide, because I realized that I come back to this, is that one of the theories out there for, or at least one of the things we do see, at least one etiology of how people come to have autism spectrum disorder, is it appears that for many of them that they have too many neurotrophins in the brain. So we're not seeing the kind of apoptosis that we would normally see, and that is causing some difficulty where it might even be, also I've heard about this kind of overgrowth at an early stage of neural development, so that there are neurons that are kind of like, it's kind of like they're communicating, they're in the wrong place and they're communicating in the wrong place. Which I could say wrong in quotes there, because it's, this is why we often see they have some kind of synesthesia, not always, but they sometimes have a synesthesia where they're seeing lights, but it's making them hear sounds, or they're hearing sounds and it's making them see a particular color. That kind of mixture of the senses, which would somewhat be explained by this idea of neurotrophins and just these areas of the brain where those axons have found not quite the right targets, and they're also not dying, or we're not seeing the apoptosis that we would normally see. And it was Rita Levi-Montalcini who told us about a lot of this kind of apoptosis and neurotrophins, and how cells, some of them need to die off, and then how other ones survive. And if you read a little bit about her in the textbook here, it's very interesting that she was working in Europe as the Germans were destroying much of Europe at the time and killing lots of people, so focusing on her work. But she found, okay, working in the sympathetic nervous system, that the sympathetic nervous system forms far more neurons than it needs. When one of its neurons forms a synapse with a muscle, that muscle delivers, in this case, a protein, the neurotrophin nerve growth factor, or NGF. We will come back to that a couple of times throughout the semester, which promotes the survival and growth of the axons. And then neurons that don't make contact with the appropriate postsynaptic cell, or the ones that are arriving later, so they're just not as strong synapses, they are going to die in a process called apoptosis. And again, as suggested by, I can't remember the authors who discovered the relationship between neurotrophins and autism, but this apoptosis is really important. We need to get rid of the neurons that are not working, because we are creating more neurons than we need. So all of the areas when they are developing in the nervous system are forming far more neurons than they need, and that apoptosis and synaptic pruning, all of that loss in a particular brain area is really indicating maturation. And so I think we do a really small bit on adolescents and older people as part of this development of the brain. So for example, teenagers are going to lose cells and parts of their prefrontal cortex, and this occurs up till about age 25, which is why I do that thing at the beginning of my classes sometimes of, this is the time for developing your prefrontal cortex. You want the appropriate connections to survive so that you are able to do things like regulate your impulses, regulate your emotions, consider other people, think about your future and your goals instead of this kind of immediate gratification. All of that is still developing up to around the age of 25. And again, part of what's really important to remember is that their neurotrophins are necessary for the survival of neurons and essential for the growth of axons and dendrites to form new synapses and learning. And so I don't think it is nerve growth factor, which is one of our neurotrophins that we see, especially as the brain is developing. I think it's the brain-derived neurotrophic factor that I come back to, again, when I talk about the hippocampus, that this is allowing for those neurons to survive in the hippocampus. We don't just want neurogenesis. We don't want just proliferation. We want the neurons to be used, and the ones that are useful, we want them to survive. So I'm stealing a quote that is in your textbook from Lewis Wolpert, 1991, who says, "It is not birth, marriage, or death, but gastrulation, which is truly the most important time of your life." Gastrulation is this time of brain development that is happening early during the embryonic period. So when our prenatal baby is still an embryo. And I have added this picture at the bottom this semester. I think it's important to just realize that there are times when any kind of teratogen is going to potentially be harmful to the physical forming of something like the central nervous system, the ear, the eyes, the arms, the legs, the heart. They have these critical periods where it's very dangerous to have teratogens in our bodies if we are pregnant. And teratogens are defined as any behavior, environment, bodily condition that could be harmful to the developing organism. And so this can include illnesses, infections, malnutrition, toxic chemicals, drugs, and even we can talk about stress as a potential bodily condition. Some amount of stress when you're pregnant is normal, but there are amounts of stress that can be harmful to the developing organism. And it's not that later on that the brain is not sensitive, but later, if we have teratogens later during fetal development, it can influence the functioning of these systems and these organs and so forth, and these structures. But it's during the embryonic period that it is the forming of those structures. And so you can see the central nervous system up there at about 3 to 6 weeks, or 2 to 6 weeks in there. It's a very sensitive, very vulnerable developing brain. And while I mentioned several different kinds of teratogens, and you can go look up all of the different possible difficulties of being exposed to something like cocaine or lead or stress or malnutrition, lack of folic acid, all of that on this developing brain. But your author stays with the fetal alcohol syndrome and goes into that in a little bit more depth, where with fetal alcohol syndrome, we see a person who grows up with some hyperactivity, some impulsivity, difficulty maintaining attention. They often look pretty ADHD and get diagnosed with ADHD, even though it's really this different etiology than a lot of people come to ADHD with. There potentially, it varies a lot how severe this fetal alcohol syndrome is, but varying degrees of mental retardation are possible. Motor problems, they have heart defects, are more likely to have heart defects as they get later in life, And they also have these facial abnormalities, which I usually go through a little bit of my how really hard this is. It's already the mental part in dealing with the sort of struggles and challenges of trying to sit through school and the social, trying to be successful in the social world, but they have these facial abnormalities that really can cause, especially now that we know more and more about it, can cause a great deal of prejudice against them. And I sat next to a woman for 8 years working side by side, and she would comment often about another one of our coworkers' granddaughters having the facial abnormalities of those kind of elfin features, and the way her face was, that she says it looks like she has fetal alcohol syndrome. And all I could think is, I just don't like prejudice of any kind, and that child has enough of a struggle without that kind of prejudice facing her. So it really is something to be careful about for so many reasons. But this is happening. This fetal alcohol syndrome can be so severe because alcohol is suppressing glutamate. If you remember, that's a widely distributed excitatory neurotransmitter. We're going to see it when we're talking about learning and memory for strengthening synapses. So I'm suppressing that, and it's enhancing GABA activity. So gamma aminobutyric acid is a widely distributed inhibitory neurotransmitter. And what this means is those neurons are not going to be receiving they're not going to be as strong as synapses because they're being somewhat inhibited from the GABA, but also they're not receiving the glutamate, that they are not going to receive the neurotrophins that they normally would, and we see a lot more apoptosis, so just neural death in the developing brain. So your author spends a little bit of time talking about the fine-tuning of the brain and of dendrites and axons by the experiences that we are having. I've had a student in my psychology of music class ask me several times about this idea of the brain that changes itself, or how we can change our brain through experience. And it's fascinating what we can see, and it's also there are limits. But this research comes from Purves and Hadley in 1985, and they injected these mice with a dye so that they could watch the dendritic branching, okay, of different neurons and how that changes based on experience. And so this is just showing 2 different neurons at time 1 in comparison to time 2 over on the right, and you can just see that there are some of those branches are elongating, and so that's going to create more receptor sites and more ability to be communicated to from other neurons. And some of those branches are retracting as we just see this neural change based on experience. And my memory is these were adult mice. Some of the classic research that has been done in this area was William Greenough, who found that rats who had enriched cages in comparison to rats who had so paltry cages without much in them, usually they took away any kind of running devices or puzzles and things they could do as they move through, what are those called, those mazes, and they also took away social engagement with other rats. Those ones that were in enriched cages that had all of that, the social engagement, the mazes and the running wheels and places to run and do things, they had thicker cortices, more dendritic branches, and improved learning. And of course, after finding that, many people have gone in and looked what exactly was it about those enriched cages? Was it the mazes? Was it the running wheels? Was it the ability to go to different places? Was it the social world? And it all looks to be pretty important. So I have Rosenzweig and Bennett as just one example. But what they found was very important was physical activity. Having a running wheel and having room to have physical activity was an important part of the developing of an improved, thicker cortex, like a brain that's going to be better at learning. And I have here just in general in humans, we see similar results. And this is not just correlational, but experimentally randomly assigning people to certain different kinds of physical activity appears to, we see a lot of, I'm going to jump to the bottom one, that we see a lot of enhancement in cognitive processes and brain anatomy that we don't see with other kinds of, so people who think that it's important to do crossword puzzles or Sudoku and all of that, and it's not that any of that is hurting the brain by any means. And I'm sure as we're doing crossword puzzles, we're getting better at crossword puzzles. But what appears to help the most with just maintaining our cognitive processes and our memory and everything is physical activity. And I've seen one study in one of my textbooks that talked about how great it is as we age to learn new dances. So not you are doing something that is a learning activity at the same time that you are doing that that can be pretty strenuous physical activity depending on the kind of dances that you're learning, and that appears to be very helpful. And I wish I would see more research kind of on that, because I espouse this importance of physical activity a great deal, and especially, as I said, aerobic exercise, getting that blood flow to the brain and allowing for that neurogenesis in the hippocampus. He also states, as I was just talking about the crossword puzzles and not really seeing that what's called FAR transfer, that as we're training young people in Latin and Greek, we've gone through different times in our educational systems where that's what was very focused on, thinking that it would help them learn other things. Training young people in Shakespeare plays, advanced mathematics, what we see is that people learn Latin and Greek, and they are better at maybe languages or learning that kind of thing. At mathematics, we see that they get better at those kinds of problems. And I think it's a strong statement that it doesn't help at all with other things. As I don't know, as again, in the psychology of music class, and we talk about how much music might help us to learn languages. And I have seen research looking at how much learning an instrument helps us to learn mathematics, but only one study. But we tend not to see that FAR transfer quite the way we want to see that FAR transfer. It really appears to be the physical activity that is helping, and especially, again, as we age. And I have this small bit also on the effects of specific or special experiences, like specific experiences that some people are going to have, that neurons become more finely tuned and responsive to experiences that have been important to us in the past. And so experiences that we're not having, we're not going to see an atrophy of the brain. We're going to see the brain really rewire based on experience. And so some of this we see in the brain adaptation of people who are blind since infancy, that the visual cortex, I mean, it still wants to be active. It's still going to have brain activity. It's not going to atrophy. So now their visual cortex responds to Braille and to identifying other objects by touch. And so I have some people say, well, just because you're blind doesn't mean you're better at hearing or better at feeling things or have more sensitive sense of touch. And I say, well, it's not. Yes, that's true at the level of the receptors, but what's happening in the brain, you have more cortical space devoted to, in this case, identifying objects by touch. And if they have used the transcranial magnetic stimulation to inactivate that visual cortex of blind people, and they have found that it interferes with their ability to identify Braille objects. So just another piece of evidence that they are identifying their Braille using the visual cortex, as now they're not getting any visual information to it. So to continue talking about fine-tuning based on a specific experience in people's lives, where different people have different experiences, we look at musicians for a little while here. And first we see that the MEG responses, so that magnetoencephalography, where we're looking at those faint magnetic fields, their responses to pure tones are twice as strong in musicians than in non-musicians. With musical training, We see an enhanced responding in subcortical structures to musical sounds and to speech sounds. I have a picture there of some of the areas that are larger in musicians than in professional musicians than in amateur musicians, and larger in amateur musicians than in non-musicians. And a lot of this is, it sounds like we might see some of this. This is correlational, that maybe I went into musical training because I had an ear for sound, but there have even been studies where they have assigned young children to take keyboard lessons for a year, and we see some changes in abilities. They haven't looked at the changes in the brain, but we see some changes in abilities that suggest that this is based on experience, that it's going in that direction. And in fact, so I'm teaching the psychology of music, and we just finished our music and the brain section, which was fascinating to me and very challenging because it showed how really complex this all is. But to kind of fit in with this, it looked like musicians had, their auditory cortex was 130% larger than the auditory cortex of a non-musician, and that what they're being helped with, what we're seeing a larger response to, is to musical sounds. Speech sounds have some overlap with our intonation and prosody, and changes that are kind of similar to some pitch changes, but that non-musical sounds, so animal calls and so forth, that's not, we're not seeing the change in response to those non-musical sounds. And finally, he goes into brain reorganization, how it can go too far with this focal hand dystonia. This he talks about on pages 129 and 130, and usually I put up these pictures on the overhead projector. A picture really does say 1,000 words here as what it shows, and the only thing I could get close to doing it with was to show this from the neuroanatomy section again, where if we stay over in A, in the somatosensory cortex, I think it's A. Is it A or B? He is talking about A because it's the feeling of the hand. That we have this homunculus, right? And part of that representation in the brain is the hand, and then we have the fingers and the thumb up there. And for people who have musical training, we see this area grow because they are feeling their hands so much when they are playing those musical instruments. And when we see brain reorganization go too far, brain reorganization is usually helping us, but in this case we can see a focal hand dystonia, where really what's happening is we'll see a particular part of the brain that is responding to more than one finger at once, as they are both reorganizing such that what's responding to the, let's say, the index finger and the middle finger are, both of those areas are growing, but if they grow in such a way that they overlap, it gets more difficult to tell them apart. And so we can see this kind of, sometimes they talk about having a rigidity in their hands, like a very uncomfortable feeling, and sometimes they have a hard time moving one finger without moving the other. So this can happen to musicians, and it sounds to me, if I remember, there are particular exercises they can do. I've been asked this a few times by students, particular exercises they can do, and I think there are ways to stimulate. So I think it's little electrical stimulations to those fingers, but don't quote me on that. I mean, we can help it, but it just can happen when we are using our hands in such a way, and when our brain is reorganizing.